And in this paper, a key contribution is defining this. How do we define the differential or the partial derivative of this with respect to this? And this is based on a proposition, I think, where this defines there is a is defined with respect to the log actually, and delta log of this with respect to this probability is this fraction. So okay, we can go on one by one. So I is basically interpretations or various possible assignment of the variables to values, and I entails O is that observation. So here you're saying for all the interpretations where I entails what you observe, and with respect to and where I entails the particular like the C is equal to V, that means when you say D1 equal to 0 or D1 as the digit D1 0 or 1 or whatever, that one. So you consider all possible interpretations. So basically you're saying select all those models, the answer sets where the observation is true, and because you are doing partial derivative, this part is true. So in that, over those models, you sum it up and say, find the probability of these interpretations divided by the probability of these interpretations and the probability where this value is true. So let's look at this example. I think it will be clear. So there are two things. So suppose I have, if you remember, so digit D1 is say, say digit D1 is equal to 2, and then the sum is addition D1, D2, D1, D2 is say 5. So here, this part is the O. This is the observation. And this is the C equal to V. This is C equal to V. Okay. So you are trying to say, okay, in how many of the places where you have the value digit 2, in how many of them this observation is true? Or so that's the ratio that is being calculated here, right? And here you are saying that minus the I V prime. So V prime some other values. So you're looking at for all the you're looking at in all the other places where you have a different value than 2, yet so V prime is different for different value, yet the addition gives you 5. Okay, you consider those ones and find the ratio there, and so that kind of gives you the kind of a partial of saying like how important this 2 is, because here using 2 you are getting 5, here without using 2 you are getting 5. So that difference is kind of in some sense the differential, and then this is normalization constant, and so and that gives you the partial derivative. I think that gives a little bit of intuition, right?
Hey, quick question.
Yes.
How many interpretations are you summing over here? Or at least like, how big is this space of interpretations?
I mean, in this particular case, the space of interpretation I is basically the total number of possible answer sets. So in this case, there was 100. And that is one of the drawbacks, is computing this is kind of a, you have to really compute all the answer sets. So right. This simple example, it was 100, but if we are thinking of the Sudoku is a much bigger deal, right? Sudoku the next one is a much bigger deal.
Yeah, and for the MNIST addition problem that we discussed previously, we consider all the stable models that satisfy O, and here O is the observation, like addition D1, D2 is 3. So basically, in that example, if we want to find all the stable models that satisfy this O, there are actually 4 stable models. So,
right, but to find out, right. You have to consider all of them.
Yes, right.
Find which 4, you have to check all 100 to find which 4 you have that.
Right, right.
Okay.
Yeah, we have a question in the audience.
Yeah, please.
What is the theta?
So say it again.
What is the parameters of theta?
So what are the parameters of theta? Theta is basically the parameters inside the neural networks. So it depends on what kind of like, I mean, if it is a convolutional neural network, all the parameters there.
Okay, so why are we doing like partial theta? I kind of don't understand behind about the blue one that you highlight.
Okay, look at here. I mean, our input is here, output is here, right? So if we are going to do the back propagation, so we are going to find this change here with respect to the parameter here, because this is what we are going to update. There is nothing here that gets updated. This is just logical part. The only parameters are here in this framework. I mean, in the previous classes, you had logic programming rules where you could the parameters were here and you could make changes. So here there's a clear separation between the neural network and the ASP part.
Thank you. Another one.
So this is an interesting example extension. That was a little toy, but this one is more interesting. Is Sudoku? Think of
Hey,
Sudoku.
we have one more question.
Yes, please.
So can you go to the previous slide?
Yeah.
So in that, so if the digits are 2 and let's say 3, which adds to 5, in the first term, do you take the probability of each digit and sum it up? Like, what's the probability of getting a 2 if the addition is 5, and what's the probability of getting a 3 if the addition is 5, and subtract the remaining all probabilities? Is that how you do it?
So here, you are doing with respect to one of the probability. So you are going to do the partial derivative with respect to say digit equal to 2. Okay. So now, so that is the P is, that's what here P denotes that it has digit is 2 or digit is 3. So you are doing partial derivative with respect to one of them. And then this parts I explained. So is digit. So you look at here in this part, consider all the places where the interpretation, the sum is 5 and the digit is 2. And yeah, so this part I already explained.
So what does the summation indicate in the first term?
So summation here, this one, right?
Yeah.
So sigma I entails A. The interpretation entails that O means this, that the addition will be 5. So all the answer sets where the addition is 5 and the digit is 2. So you're looking for all answer sets of this kind. So there will be basically one answer set where of this kind is that this digit D2 has value 3. Right?
Yes.
And while in the bottom part, it's saying look for all the answer sets where digit D1 is 2. So there will be 10 such answer sets because the digit D2 can have 10 values, 0 to 9. So there will be 10 answer sets over which you'll add the probability here. There will be exactly one answer set where you have the probability here. While in this case, so this part is you are considering all the ones. So instead of 2, you are considering all the 0 to 9 without 2. And you're saying, okay, in those ones, how many players where the sum is going to be 5 and the all the possibilities where it is not 2. So you'll calculate that one. You have to think a little bit more to see how many probabilities here and here.
We'll take one more question.
Yes.
I cannot help but notice the similarities between mutual information measures in your derivative. Like, did you think about that while coming to it, or is it something that you came up with independently from that?
Jun, you can answer.
I'm sorry, I didn't didn't hear that clearly. So could you repeat the question?
In the derivative, in the numerator of the derivative, we can see that it's the difference between the sum of the probabilities, right? So
right.
how did you come to that? How did you come to that measure? Like, did you think about the end results of analytical mutual information measures, which gives you this kind of measure that log of probability by probability gives you a difference? Like, did you come to that in that sort of way, or did you come to that independently?
Still quite don't, but maybe I can make it clear here. For this computation, it's all done not in neural network, but in Python. So what I did is basically I first compute all the stable models such that I satisfy all. And then I split all the stable models I into two parts, which is the two terms in the numerator, left and right. So one part is that those I's agree with the atom, like digit D1 equals 2. And the second part is those atoms in stable models that doesn't agree with this atom digit D1 equals 2. And basically for those stable models that agree with that, I increase, it will contribute to a positive gradient. And for those doesn't agree, it will contribute to a negative gradient. And that's how the numerator is formulated.